So last time, we started talking about this idea of quantifying uncertainty, right? And I posed the question that in practice we get a numerical matrix X, a numerical vector Y. We solve for, let's say, either the normal equations or in the case where X transpose X is invertible, we can write a closed form formula for beta hat. We plug it in. We get a numerical value like what we have down there. Beta hat. So then, where is the uncertainty? How do we? What do we mean by quantifying uncertainty variability? So let me ask you guys, see if you remember. So it's a very important kind of concept to understand. Otherwise, you'd remain confused throughout the majority of statistics. So it's like p-values, confidence intervals, everything is confusing unless you understand what we're talking about here. So what do we mean by uncertainty? Like, how does it like not contradict observing? Yes.
The uncertainty is in the epsilon, the noise term, not in beta X. So
But I plug in X, I plug in Y, I get a beta hat. So my beta hat is very certain. So the noise is in the epsilon. I don't see the epsilon. So epsilon is noisy, but beta hat is good. So what's going on again? Let's see if anyone can like convince me that there is something that we have to like. Otherwise, we can just say we're done. We estimated beta hat. Let's go home, right? There is noise in epsilon, but I want a little bit more nonce. So let's say, where is the uncertainty? So we have this model, right? Y is equal to X beta plus epsilon. So let's say epsilon is the noise, but I get to say a Y and an X. In your homework problems, you get a Y, you get an X. The Y supposedly has the noise, but I get a single Y and a single X. When I plug it in, I get like a numerical beta hat. So where is the uncertainty that we're talking about? It's related to like an abstract notion that we talked about, right? Towards the end. Like, yeah. Does anyone remember it's like the last half of the last lecture? So the idea is that we model Y and epsilon potentially X's as random variables, right? So what does it mean that they're random variables? They have distributions, yeah. So, but they're abstract objects. So random variables, you have to be able to like conceptualize these random, like these abstract objects. You're not going to get the random variable, so you're going to get realization of the random variable. So every like time you do the experiment, you assume that you're observing a realization of this random variable. The distribution tells you like the probability of observing certain values, right? The probability, again, we usually interpret as the frequency of like how many times you observe this particular value if you repeat the experiment many times. So these random variables are abstracting away what happens when you do the experiment many times. Okay, so there is the numerical y and x, and there's the abstract random variable y and potentially x. So in this course, like we usually assume x to be fixed, deterministic. So y is going to be a random variable. Epsilon is going to be a random variable. So there is the realization, which is the numerical thing. And then there's the abstract random variable, which is the thing that you can't like numerically show, but it has the distribution. It like characterizes what happens when you do things not in a larger scale. So I'm trying to make sure that you understand the distinction. Otherwise, everything would be confusing. So a lot of things that we're going to do today and later are working with these abstract random variables, not the numerical values. But then you apply it to the tests that we like develop, or the confidence intervals you apply it to these numerical values, to these realizations, you get a realization of those abstract objects. So yi, let's say, is going to be a random variable. When we talk about random variable, we're now in the abstract domain. Okay, very abstract. Y is a random variable, like y is a random variable, so they're going to be, if you put them together, you get a random vector, and then the randomness is going to come from epsilon, as was pointed out. Epsilon is going to be a random variable, so it's going to have a distribution. If I put them together, epsilons into a vector, so we're going to put y into a vector, epsilon into a vector. Now I'm going to characterize what this random variable is. We're going to put assumptions on it. We assume that the expectation is 0. Again, expectation is an abstract, so the property of the abstract object. Covariance is sigma squared in. Covariance matrix sigma squared in. This is one assumption that we put. The second assumption is that epsilon is normal, means 0, and covariance sigma squared I. Okay. And under these assumptions, then y will have, so if I characterize a distribution or statistical properties of epsilon, because y is derived from epsilon, and x is fixed and data is fixed, y is going to be a random variable, it's going to have a distribution, it's going to have like expectations, covariance matrices, and because beta hat is also derived from y, beta hat will be a random variable, so we'll have a distribution. It will have all sort of statistical properties. Okay, so all of these quantities will be abstract random variables as well. And then we can talk about like the variance of the components of beta hat and so on and so forth. Okay, sort of clear. Numerical realizations versus the abstract random variables. I'm gonna like repeat this until like everyone just can recite them from heart. Okay, it's a very important distinctions, and just once you like put some clicks, just everything falls into place. Otherwise, you'll be confused all the time. Sounds good? Okay, so this assumption E2 allows us to do a lot because this characterizes the entire distribution. And if you have gone to the discussion yesterday, hopefully Jan talked about maximum likelihood estimation. So we can use this to drive the distribution of y, and then do the maximum likelihood estimation of beta and sigma squared. So sigma squared is going to be an unknown parameter, beta is an unknown parameter, x and y is going to be observed. So used to our unknown parameters, we want to estimate, we have an estimate of beta via the least squares, which we sort of arrived without any distributional assumption. It's a reasonable estimator. We also did the geometric interpretation, but there is like a statistical procedure, maximum likelihood, that we can do. So how many people went to the discussion? So how many people saw the maximum likelihood? Okay. I'm going to ask you shortly to tell me about it. We don't have time to go through the details, but for doing maximum likelihood, I would have to specify the distribution of y, for example. Okay, so let's say I assume E2. Can you tell me what the distribution of y is? And I can write down the likelihood based on the observation of y, and I can do the maximum likelihood. So what is the distribution of y? Normal? Who's talking? Yes, okay. So, okay, let's try. let's try this. So normal would mean so for like under E2, y is normal would mean and correct.
Sigma squared.
So why is that?
Well, because y is equal to x plus that.
Yes,
And that has a distribution of normal 0. Sigma squared.
yes,
And so y has a shift of x beta. So you shift it, and x beta is it's non-random.
it's non-random. Yeah, so it's a non-random shift added to epsilon.
Yeah, and then when you do expectation, it's just itself.
So then you take the expectation. Expectation is linear. The expectation of the first term is itself plus the expectation of the second one, which is 0. Yes,
And then for the variance,
covariance.
this shift, the covariance, the shift doesn't matter.
Yeah, so the covariance matrix is invariant to shift. So the covariance matrix of y is the same as, so y is a constant shift of epsilon. So covariance matrix of y is going to be the same as covariance of epsilon because covariance matrices are matrices are invariant to shift, to the constant shift. So, and the mean is going to be, as was pointed out, is going to be x beta plus the mean of epsilon. This is by linearity of expectation. And so this would be x beta. So, but, okay, so these would like, justify these two statements, but why is it normal? Why is it multivariate normal? Epsilon is multivariate normal. And how is y related to epsilon? We have to like argue.
Oh,
So say y was like sine epsilon 1 plus sine epsilon 2 plus, like it can be like that because I sine epsilon 1 like cosine epsilon 1 up to sine epsilon and something like that. Would it be normal? Y would be like epsilon squared, epsilon 2 minus epsilon 1 to the third, and so on. Yeah, none of these would be multivariate normal. Yeah, so it's, yeah, so it's something about linearity. So a linear transformation, or in this case, an affine transformation, because it's like B plus identity times epsilon. So it's an affine transformation. Affine transformations of normal random variables are normal. And so Y is an affine transformation. Of a multivariate normal vector epsilon. Okay. And so it's multivariate normal. So all the pieces are justified. So it's multivariate normal because it's an affine transformation of multivariate normal random variable, which is epsilon. And the mean and the covariance we know how to calculate. Okay, so Y will have that distribution. Everyone happy with this? So it just puts everything that we did together. The affine transformation is very simple. It's just a constant shift. But if I had like x beta plus some a times epsilon, it still would be multivariate normal. So once I have this, for example, I can do maximum likelihood. So now that you have seen it, maybe tell me how to do maximum likelihood estimation of beta very quickly. What is maximum likelihood? What is the likelihood? It's actually, what is the likelihood? It's another confusing concept in statistics. Yes.
It's the distribution function, the joint distribution function of
It's very close, but the distribution function, joint distribution function of all the variables. Let's say the PDF, the joint PDF of y. But still, like, I need a little bit of tweaking. That's not quite the likelihood, okay? So if you view it as the function of the parameter, that's the likelihood. So likelihood for statisticians is a function of the parameter. So if I write down the joint distribution, so we actually have this here, I'm not gonna write. So we covered almost all of this. So if I write, so y is x beta, so this slide is basically summarizing. So mu here is x beta. So we know that y is mu sigma squared I. I can write the PDF, if you remember the PDF of the multivariate normal. I have to plug in the sigma squared, capital sigma, which is the covariance matrix in here and in here. I'm plugging it, it's identity sigma squared. So think simplify, you get to this. Okay, hopefully you've seen this. And then I plug in y as like mu is like x beta. This is going to be the PDF. So this is really the PDF of y. But the idea is that the PDF, if you view it as a function of the unknown parameters, sigma squared and beta, that's called the likelihood. Okay. As a function of sigma squared and beta, it's not a probability distribution function. So it doesn't integrate to one, for example. Why is called the likelihood? Because I can change the parameter. So think of the PDF as like sort of the probability. It's not the probability, it's like probability density. But if this is like f of y, f of y, sometimes people write it like this, f of y given beta and sigma squared. So this is really f of y. If you view it as a function of y, it will be the PDF. The statisticians view it as a function of beta and sigma squared, so you sometimes write that L beta sigma squared given y. This is like a statistical notation. It's the same object, but view it as a function of the parameter. It's called likelihood. The reason why we view it like that is because y for a statistician would be fixed at the observed value. Now I'm going to change the parameter, see which parameters make this larger. So the parameters under which this is larger, this is sometimes saying like the probability of that observation is higher under that model. So I want to find a model for the parameters under which I have higher probability of observing y. Okay, so you view this as a function of the unknown parameters. There's a very subtle distinction, but it's a very useful distinction. So likelihood is like the PDF viewed as a function of unknown parameters. Okay, likelihood. Is the PDF of, let's say, y for observations viewed as a function of unknown parameters. So the likelihood principle tells you find the model whose likelihood is highest, or like try to maximize the likelihood among the, so different parameters give you different models. So beta and sigma squared sort of give you remember the beta determines the slope of the line, or the basically cost slope, the hyperplane. The different data give you different models for the data. And so you're going to pick the model, the parameters to maximize the likelihood. Probability, if you want. Infinitesimal probability. The probability is really this. So Fy beta sigma squared dy is like sort of approximately probability of observing y under model beta and sigma squared. Sort of clear? So then the MLE, maximum likelihood estimation, is trying to maximize this. So if you pick sigma squared, try to maximize beta, you get the least square solution. Hopefully, Jan went over that. You take the derivatives that are equal to 0, you get the normal equation, and you can invert it. If you can invert it, you get beta hat. Once I have beta hat, I plug in beta hat into this guy, the likelihood now I can maximize over sigma squared. If you plug in beta hat and try to maximize over sigma squared, you can also get an estimate of, so it's a geometric interpretation we talked about, sort of. Once you plug in beta hat in here, you try to maximize over sigma squared. This thing is really just y minus x beta hat. I'm going over it rather quickly because I hope you've seen this before in the discussion. So you put the beta hat there, you maximize over sigma squared. Again, it's an optimization problem in a single variable. You can do it by differentiation, set it equal to 0, and verifying it's actually a maximum. The solution turns out to be this guy. So sigma hat squared would be, the MLE would be like basically y minus x beta hat. So that's s beta hat, y notation here, which is a bad notation. So so that would be the MLE for the sigma squared. So you can calculate that your estimate of beta hat. Y minus x beta hat is the residual, if you remember. So x beta hat is the fitted value. This is the fitted value. This is the one that's on the line. And then y minus mu hat squared, the normal squared is just some of the squares of errors of the regression. So basically some of the residuals, so you can write it as this. So E is basically y minus x beta hat or y minus mu hat if you want. So the norm of the residual squared divided by n, it's basically sort of some sort of average of the I squared. So that's an estimate of sigma hat. Yes, right, sigma.
So to calculate that, so mu hat is just when you calculate your beta vector, mu hat is just the corresponding one to the y.
Yeah, mu hat is just x beta hat. Yeah.
Okay. And then what does S of beta hat mean? Like when you said.
So S beta hat is yeah. So I should have not introduced the notation. So S beta is just your book's way of writing this quantity.
Oh, okay.
Right, y minus x beta for any beta. Particularly if I said beta hat in there. This beta hat would just be y minus x beta hat. It's just a shorthand for writing that. It's not a good notation. I would prefer just writing normal y minus x beta squared. It's just to simplify the notation. In any case, so the thing that at the end of the day, your maximum likelihood estimator of sigma squared would be this. So MLE is interesting because it gives you an estimate of sigma squared. This is sort of reasonable. You could have come up with this because y minus x beta, where beta is the true beta, would be epsilon, right? So if I had the true beta, sometimes I write it like this, remember? So if I actually had the true beta star, I could form y minus x beta star. That would give me epsilon. And then the norm of this, so basically if I square each element, so let's do this. A little bit hard to do here. We do. We just and a page here. It's down here. So if you had like the true model, if I had access to the true beta star, then I would form y minus x beta star. That will be epsilon. Okay, so it would be good to estimate the variance of the noise by something like this. Because the expectation of this would be, anyone knows the expectation of this? So let's say epsilon is normal 0. Sigma squared. Is the expectation of this? Yeah.
0.
No. That was a short answer and a short response.
Not, no, I thought if you take epsilon and square it, the distribution stays the same.
No, the distribution doesn't stay the same for square things.
Well, because essentially at zero, the mean doesn't change.
The mean certainly changes because the mean, so epsilon is like can be positive and negative. When you square it, it cannot be negative.
Oh.
So if you have a Gaussian, let's say if you have a like a univariate Gaussian, when you square it, the distribution would be like here. So it would like be something like that. So if a non-negative random variable is like sort of the expectation is zero, it has to be zero. But we're getting close. That's a good a good mistake to make because you realize that the sign matters. Squaring the square, so this guy epsilon I squared is not going to have a normal distribution. Anyone knows what the distribution epsilon I would be? So suppose I have, let's back up a little bit. Suppose I have epsilon I is normal, which means 0 and 1. Forget about the sigma square. What will be the distribution of this? Good, yeah, this is going to be chi-squared with 1 degrees of freedom. Distribution changes. So what will be the expectation of epsilon I squared? Is related to the variance, if you remember. What is the formula? There are two formulas. Who's that?
It's equal to variance of epsilon minus expectation of epsilon squared.
Great. So what is expectation of epsilon?
0.
So this is 0, so it will be equal to the variance.
It's going to be variance of epsilon.
Yeah, so it's going to be 1. So the expectation of epsilon I squared would be 1. So the expectation of chi squared 1 would be 1. In our case, each one of these, so if I assume something like that, if you recall, epsilon i's are normal. Can you tell me what the individual ones are going to be? Standard will be, yeah,
0 sigma.
0 sigma squared, and we also have their IID. So this has a lot of information. Remember, the covariance tells you about independence in the normal term. Because the covariance is, cross covariances are 0 between the elements. All of them are IID, don't mean 0. Very sigma. So what is the expectation of epsilon I squared? Escape. Same argument. Sorry?
Sigma squared.
Yeah, so it would be variance of epsilon I minus the expectation of epsilon I squared. So this would be sigma squared. Right? So now what is this quantity? Yes.
Sigma squared over.
Sigma squared over n squared.
Yeah, n squared.
Why?
Because the 1 over n takes the square factor. Of just
I can't understand why. So this is 1 over n.
no, you pull the 1 over n out, so it's just sigma squared.
Okay, so let's pull this out. That's step by step. So pull 1 over n out. I get something like that. What is the next step?
Absolutely, the sum of all the sigma squared, which is n sigma squared.
Sum comes out as well because the expectation is linear. So I get this.
So the sum would just multiply that expectation by n.
Okay, so this would be n by sigma squared.
And then dx.
Okay, so what's the end result?
So sigma squared.
Sigma squared. Okay, so the expectation of this would be sigma squared. So if I had epsilon theta star, I would form this. I would have access to epsilon, and then this would be an unbiased estimator of sigma squared. Unbiased means the expectation would be equal to sigma squared. So this would be a good estimator, and in fact, it concentrates. You can calculate the variance of this, and the variance of this goes down like 1 over n. So the variance is going to be very small. So it's very close to sigma squared in fact. So this is it. We can go over this later more. So you calculate the variance. So we have calculated the expectation of sigma squared with the variance that you calculated would be the fourth moment of Gaussian times sigma to the 4 divided by n. So it goes down like 1 over n. So it's concentrated actually near sigma squared, so it's a very good estimator. You don't have access to this because you don't have access to beta star. What the maximum likelihood estimator tells you is that it's fine, just plug in, instead of in this formula, instead of like using beta star, just use beta hat. So if I use beta hat, so we don't have access to, we don't have access to beta hat, beta star, but MLE suggests forming y minus x beta hat. Now this is not going to be exactly epsilon, it's going to be e. E is just a residual. So there is a distinction between the residual and the actual error. The residual is what you get to observe based on your estimate of beta hat. It's like supposed to be close to epsilon, but it's not. It's something different. And then you form 1 over n summation I from 1 to n. EI is squared. So that would be your estimate of the variance. Okay. Good, i.e. unbiased, and highly concentrated. Estimate of the variance, noise variance, but we don't have access to it. We have access to this. It's like a natural thing to do. So divide 1 over n. Just replace e with this epsilon, like epsilon with this e, and it's like suggested by the MLE. So suggested by the MLE. So just justification is sort of clear. The distinction between epsilon and e is also clear. So the error is like this epsilon is the unobservable error. So you can observe it if you know the true beta star. This one you can observe because you can have y, you have x, you fit the model, you get a beta hat, you calculate this residual. So e is like the surrogate for epsilon. So you calculate, you come up with this estimate. Sounds good? It's good, but it's subtle. So this is no longer going to be unbiased. So if you calculate the expectation of this, it's not going to be equal to sigma squared. This is the fun part. Anyone can like tell me why? Probably not, but let's try. These are not going to be independent. So the distribution of this is tricky because this is based on beta hat and beta hat is based on y. So there is dependence between beta hat and y. When you construct this E, that you introduce a lot of dependence. So it's not easily, we can't say that the I's have like this distribution. They're not going to have the same distribution as this. You're going to see what the distribution of the I's is. It's going to be still normal. It's going to be normal because you'll see when you plug things in, E would be just a linear transformation of Y, that would be normal, but the covariance would be like a little bit more sophisticated. Because the covariance is different. It turns out that this is going to be not equal to. So this when you calculate the expectation is not going to be exactly sigma squared, it will be something else. And you sum, and then it's going to be different. Okay, so we sort of get to it. Yeah.
But that actually shows sigma hat squared, right? The sigma hat.
Right. Yes. So not an unbiased estimator. We will see that the distribution of E shortly. And what will be like anyone knows what an unbiased estimator would be in this case? There's a bit of tweak that I have to make to this. Probably I've seen it in like some previous course. We'll see later. Yes.
Last quarter we used S squared, we read by n plus 1 instead of n.
Okay, great. And divided by what?
We did 1 over n plus 1, I think.
N plus 1. You divide by something, but it's not n plus 1.
It was adjusted by something.
Adjusted by something. So anyone remembers that something?
Was it n minus 1?
Slightly better. close, but more general.
Is it n minus p plus 1?
Okay, good. N minus p plus 1. So you have the number of parameters in the model is p plus 1. You have p betas and then an intercept, which is p plus 1. So you subtract that many free parameters that you have. So the model has p plus 1 free parameters. This is sample size. You divide by this. This turns out to be unbiased. So if I form this, instead of dividing by n, divide by this, this turns out to be an unbiased. So if you can prove that this is unbiased, you learn a lot, like you've learned a lot in this course. You may or may not do it, but we'll stick with this. You can also do this. The MLE for sigma squared is going to be close to this if n is very large. If n is very large, p is small, let's say p is 2, n is 1,000, the difference is minor. But then the sample size is small. Some people prefer this. If you prefer unbiased estimators, it's a different story whether you have to prefer unbiased estimators. It's debatable, but this is very common. So in R, like our statistical packages use this estimate rather than that. We get to why this is the case, but this is going to be s squared. So I'm going to use s squared for this. And you can also write it as this is norm e squared, remember. Okay, s beta hat I don't like, so let's do e squared. So the difference between the MLE is this guy, s squared is that guy, we're going to go with s squared. S squared is unbiased, both maybe see. Sigma hat is not unbiased. Okay, so sort of okay. So that's how you estimate the noise variance. You also know how to estimate beta hat. The OLS estimator is for beta hat can be justified in many different ways. We did it via the usual like least squares idea, geometric interpretation, very important for us, via projection, and also you can do it with the MLE, the details like Jan went over. And then once you have that, you can continue with the MLE, figure out the MLE of the rest of the parameters, in this case sigma squared, you get the MLE the MLE for sigma squared is this, but then you just cross it, work with the unbiased system. Later we'll see why this is a biased system. Okay, sounds good. Now what I want to do, any questions? Questions, comments? What I want to do is like to calculate the statistical properties. As I mentioned, these estimators, beta hat, epsilon hat, even E, these are now like switch to the abstract view. These are all random variables. They have variances, they have covariances. We can talk about unbiased. Unbiased is an abstract property. Expectation is an abstract property. When you say unbiased, you can't like observe unbiasedness in a single realization. Unbiasedness is a property that you see over many, many, many times. So we're going to talk about these. And I have to fill in some of the details that we glossed over. So just maybe before doing that. So this summarizes our assumptions. E1, under E1, we have that the noise vector is zero mean covariance sigma squared. And I forgot to mention, we're going to assume that epsilon i's are usually independent under E1. For E2, we have the distribution assumption, which is like the entire distribution is given by the normal, multivariate normal, with the corresponding mean and covariance matrix. So E2 is stronger than E1. It implies E1. E1 is weaker. Under E1, we have the expectation of y is x beta, something where it is mu. Covariance of y is sigma squared in. Under E2, we have the whole distribution, which is x beta sigma squared in, normal between x beta and sigma squared in. We did this. X is the design called the design matrix. This is the thing that I glossed over. We also assume that usually that X is full rank. So X is n by p plus 1. Remember the rows are The rows are telling you the sample size, basically the samples. P plus one are the features or the covariates. And I usually assume that n is larger than p plus one. It's just enough to say that it has full column rank. So full column rank, if you remember the rank, when you say full column rank, the columns are linearly independent, all of them. So the rank of the matrix is equal to its column, the number of columns. When you say something is has full column rank, means that the rank is equal to the number of columns. And in that case, the number of columns has to be smaller than n. Because if it's larger, so the rank of a matrix can be at most the minimum of the number of rows and columns. So rank of any matrix is at most the minimum of n and p plus one. This follows because there is one rank. Column rank is equal to row rank, and each one can be at most the number of elements of the corresponding dimension. And so the rank of the matrix can't be bigger than the minimum of the dimensions. So when we say full column rank, it means the rank is p plus one. So it means that p plus one has to be less than or equal to dimension. So this contains a lot. So the rank is p plus one and the p plus one is less than or equal to n. Okay, so you say full column rank is equivalent to saying that p plus one is less than n and the rank of x is equal to p plus one. So this is the assumption that we're going to make. And this is the setting of the classical statistics where your sample size is bigger than the number of features, oftentimes by a lot. In modern statistics, so classical statistics, or the classical data sets, some modern data sets are like this. So you have like n, 50 p plus 1 is like 10,000. This is something that we usually don't deal with in this course. This is hard. This is sort of easy. Sample size, if you have a lot more samples than covariates, the problem is easy. If you have a lot more covariates than the samples, this problem is hard. So a lot of modern statistics tries to come up with ways of dealing with this. I might talk about that. So this is like the high dimensional setting. This is classical setting. So P much bigger than N. This is N, like N much bigger than P. So for us, we're going to do that. So if you assume that the X is has full column rank, then that X transpose X is going to be invertible. This is like the fact of linear algebra. So under this assumption, X transpose X is invertible. And then I have this, from these normal equations, I can go to this. If that doesn't hold, these normal equations are still valid for the least squares, but then they're going to in general have more than one solution. You'd have multiple beta hats. May talk about that. So in the case, if the column rank is not full, some of the columns can be written as linear combination of the others, if you remember. So it's called multi-collinearity. And beta is not, the actual beta is not unique, and the beta hat would not be unique. What would be unique is the projection, which is x beta hat. So if you remember the geometric interpretation, these the squares, we project y onto the image of x, and what you get here is mu hat, the residual would be e orthogonal to the image. This mu hat would be unique. Projection is unique, but you may have different ways of writing it in terms of the column vectors of x, if x is not full rank. If x is full rank, has full column rank, then there's a unique way of representing this mu hat as a linear combination of columns, and that unique way gives you data. Okay, so this was a little bit fast, but projection is unique. Beta hat may or may not be unique under that assumption that we have. Beta hat will be unique, and you can actually calculate it like this. Otherwise, you're stuck at this. These normal equations will have multiple solutions. You're not going to worry too much until the end. Sounds good? Assumption x1, yes.
So unless you tell us it's not full rank, we assume that it is full rank and there's only one unique solution.
Yes, yes. what will happen in practice is like numerically you're close to like full rank, but you're close to, so it's hard to come up with a matrix which is like you have to construct a matrix which is not full rank. Real data numerically usually they're full rank, but it could be very close to not being full rank. How you measure the closeness is something that you may discuss towards the end. Okay, and as this like gracefully violated, not like mathematically violated, but it's like close to being not full rank, then bad things happen. So the variances of beta hats blow up, and we'll talk about that. Any questions? So I think we covered everything here. So MLE, this is the geometric interpretation. We started with this. It's very important, and we'll come back to this if you have questions. Let me know. From this geometric interpretation, actually, a couple of things follow. And I skipped over those. So we know that E is orthogonal to the image. E is going to be orthogonal to mu hat, because mu hat is in the image. E is also going to be orthogonal to every column of X, because the columns are in the image. So all of this we can list as consequences of the geometric interpretation. So if Xj is the j column of X, E is going to be orthogonal to Xj. E is going to be orthogonal to the vector 1 if we have the intercept in the model, because this is going to be one of the columns. And E is going to be orthogonal to mu hat. So these are all constraints that you can verify. So if you fit at least the squares estimate, you calculate the residual, you calculate the mu hat, and assuming that the intercept is in the model, all of these should hold. If one of them fails, you did something wrong. Because these are checks. It doesn't have anything to do with distributions or any assumptions. It's just the properties of least the squares that follows from the geometry. For example, if there is an intercept in the model, which means there is a column of 1, that column of 1 is in the image, so E is orthogonal to this, which means that the sum of the elements is 0. Okay, so if you have intercept in the model, then you calculate the beta hat and you calculate the residual. If you sum the residual, they have to be 0. This is a consequence of the fact that the residual vector is orthogonal to the vector of 1. Why is that? Because vector of 1s would be here somewhere, because we included it as one of the columns, remember? So all the columns of X are going to be in this, including 1, and E is going to be orthogonal to everyone. E orthogonal to mu hat is like that, and so on. So you can verify this. Okay, so these are properties coming from the geometry. Easy to verify, and it can tell you whether you've done regression correctly. It's also good for exams, because I can give you something and ask you whether it's like from a valid. I don't think I've done it necessarily, but you can ask, for example, is this residual is a valid residual from a regression, or these residual match like is consistent with this mu hat. And if it fails, for example, this, then it's not. If it's satisfied, it still may not be, but gives you some checks. Okay, sounds good. Okay, so now a few more things before we get to calculating the statistical properties. So there's this hat matrix which you have seen in your problems. So if I have beta hat, under those assumptions, this is the formula for beta hat. If I calculate mu hat, which is x beta hat, you get this plug in beta hat there, and you get this expression. This matrix times y, and this matrix is called the hat matrix, and represented by H. It is an instance of an orthogonal projection matrix. So what it does is, effectively what it's doing is that you give me any y, I multiply it by this H, I get the projection. So mu hat is HY. So it projects every vector that I want onto the image of X. So it's a matrix associated with this image of X that we have. You can see it's just completely determined by X. And it turns out that it projects onto the image, because the way that we drive this beta hat, this would be projection of Y onto the image. You can see this is obtained by multiplying H by Y. These type of matrices are called projection matrices, or orthogonal projection matrices, and they have very interesting properties that follow from geometry, and you also verify it in your homework problems. In particular, they're symmetric, and they're idempotent. Anyone knows what idempotent means? Yeah, so the square of it is equal to itself. So these matrices have these properties. H is symmetric. So HY, like, for any vector y, HY is going to be the orthogonal projection of y into the image. H is symmetric, since H transpose H is equal to H. It's easy to verify from the formula you have done your problem. H is idempotent, which means H squared is equal to H. And then any matrix with these two properties, being symmetric and idempotent, is an orthogonal projection matrix. It projects onto the image of something. At least it projects onto the image of itself. Image of X and image of H are going to be the same. So any matrix is an orthogonal projection matrix if and only if it's symmetric and idempotent. These two properties characterize orthogonal projections. This idempotence geometrically is very natural. Anyone can tell me what is the geometric interpretation of this idempotence? What does it mean that H squared is equal to H? So H squared applied to Y is like H applied to H applied. So this is like that. And this is like mu hat. So you're saying this is equal to HY. Right? For any Y, which is also mu hat. So thinking of H, applying H as projection, what does idempotence mean? Geometrically. Applying it once to a vector which is outside the image of X project, yes.
Used in the image, so it doesn't.
Right. So let's say I start from Y, it could be in the image, it could be outside the image. So when I project it, if it's outside, I get something genuinely different. But now once I project it, I'm in the image. Now if I project it back into the image, anything in the image, if I project it onto the image, it will be itself because it's the closest to itself. The residual will be 0. So the second time you project, you get back the same thing. So H squared Y is going to be the same as HY, which is the first projection. And this holds for every Y, so this means that H squared has to be equal to H. So projection matrices have these idempotence properties because the second time you project, you get back the same thing. The symmetry forces is orthogonal business. It's like a side note, there are projections that are not orthogonal. So you can project along in like an oblique direction. They satisfy idempotence, but not symmetry. They together, these two properties mean that you're orthogonally projecting. For us, projection, it's just drop usually orthogonal. So projection means orthogonal projection, means that they have these two properties. The I minus H is also a projection matrix. It's very easy to verify, and you've probably done it in your problem, but this is also symmetric. It's also idempotent, so it has to be a projection matrix. What does it project onto? It projects onto the orthogonal complement of the image of X. So if I project onto the image of X, I get mu. If I project onto the orthogonal complement, I actually get E. Okay, and you can see that E, remember, is like Y minus mu, which is Y minus mu hat, Y minus HY, which is I minus HY. You can see that this residual is actually I minus HY, and in fact, E is a projection of Y onto the orthogonal complement along this direction. So if I have H applied to Y, I project onto the image. If I apply I minus H, I project onto the orthogonal complement, which actually is the residual of the original projection. So there is this duality. You can think of E as the residual projection onto the image of X, or E as the projection onto the orthogonal complement, and mu hat is the residual of that projection. For us, usually one is more important. So image of X is more important. So mu hat is the projection. E would be residual, but itself is a projection onto some other space, which is the orthogonal complement of the image of X. And it's obtained. So the associated projection matrix is I minus H. So if you recall, I mentioned that E is like in matrix times Y. That's that matrix. So that residual is connected to Y. Y is I minus H. Is it sort of clear? So these matrices tell you a lot about interesting quantity. So the fitted values mu hat is h times y, it's projection of y into the image of x. The residual is I minus h times y, it's the projection of y into the orthogonal complement. And if you remember these orthogonal complement, like image of x and its orthogonal complement, they sort of together sort of construct the entire space. So basically the summary is every vector y can be decomposed into two pieces. Mu hat plus the residual, mu hat that is in the image, these in the orthogonal complement image. We have seen this before. I'm just doing with more details. This part can be obtained by h times y. This part is I minus h times y, and basically add up to y because the hy cancels out. So that's how we can calculate these two pieces. This is related to this idea that the entire space is the direct sum of these two. Every vector can be uniquely decomposed into one component in the image of x, one component in the orthogonal component of the image. And these components can be obtained by applying these projection matrices. Just one of them defined, the other one is I minus the other. Okay. You also know more from your homework problem, if you remember. Anyone knows what the eigenvalues of H are?
One is 0.
1 or 0. So these projection matrices have this interesting property that the eigenvalues are either 0 or 1. And this follows from idempotence. If you go back to your homework problem, use this idempotence, you apply the spectral decomposition, it gives you some equations for the eigenvalues. H has eigenvalues in 0 to 1. The number of zeros, if you remember, the number of non-zeros tell you something about the rank. So how many non-zero eigenvalues it has, how many ones it has among the eigenvalues tell you the rank of H. The rank of H is going to be equal to the rank of X. If X is 4 rank, you can have exactly p plus 1 ones. I might come back to this, but there's a lot that you can know about H. Let's say this. The rank of it, or the rank of X, rank of H would be equal to the rank of X, because remember the rank of X is basically the dimension of the image, and this is sort of projecting onto that image, so it's going to see everything in the image. So the rank of H is equal to the rank of X. General. In our case, this is going to be p plus 1 under x1, assumption x1. And so this would be the number of eigenvalues of H that are equal to 1. So it's a lot of information, but sort of half of it you've seen in homework 2. Now is a good time to go back, redo the exercise, or just in light of this, review that exercise. You see a lot of the properties. Come on, questions? Okay, let's move on. There's another matrix which is of interest. Very quickly mention it. This matrix in the middle, this guy, X transpose X. So H is going to be n by n. So this is like n by p plus 1. On the other side, this is going to be p plus 1 by n. So H is going to be an n by n matrix. Similarly, I minus H is n by n matrix. This guy in the middle, X transpose X, is going to be p plus 1 by p plus 1. It's a small matrix. If you write down the columns of X as x0, x1, x2, up to xp, it's not hard to see that the ith element of this X transpose X is going to be xi transpose xj. So it's the inner product of xi, xj. So the ith element of X transpose X give you the inner product of the columns of X. These matrices are called Gram matrices, and because they're related to the Gram-Schmidt procedure, sort of, I believe. You may be mistaken. In any case, so the entries are pairwise inner products. So this is often something that you use in the exams. I give you the inner products, you can construct this. So if you see the slide, if you see me in the exam, I give you something like, I give you the inner product of these elements, you should be able to compose X transpose X. It's an easy way of giving you X transpose X. And also knowing that you understood this part. So it just gives you pairwise inner products. For example, if the ijth elements are 0 for everything off diagonal, it means that the columns are orthogonal. So if you have a design whose columns are orthogonal, everything outside the diagonal will be 0 because they're going to be like inner products of different columns and it will be 0. Hopefully on the diagonal things are not 0. On the diagonal they're going to be the norms. So X transpose I would be just the inner product of xi and xi, which is going to be the norm of xi. And if it's 0, you're in trouble because that entire column is going to be 0. Usually that doesn't happen. If the entire column is 0, the rank of x collapses by 1, which is not something that we want. So usually you don't have 0 diagonals, but off diagonals could be 0. You get an orthogonal design, which is desirable because then I want to invert it. If it's diagonal, it's easy to invert. So for orthogonal designs, I can easily invert x transpose x. It's much easier to calculate beta. So you might see these in the exams or homework problems. Another example, like or like exercise very quickly, matrices that look like this, x transpose x, are always positive semi-different. You can show this from, based on the definition, show this as an exercise. So gram matrices are all positive semi-different. So if you see a matrix can be written as x transpose x for some x, then it has to be positive semi-different. The fact that the rank of G is also equal to the rank of X is something that I mentioned. Here's the proof, you can just read it, it's optional. But because we're assuming that X is full rank, rank is equal to P plus 1, and the rank of the gram matrix is going to be equal to P plus 1. And this is a square matrix, P plus 1 by P plus 1, which is full rank, then it's invertible. So that's why you can invert it, we have beta hat and stuff. So this was like a quick introduction to gram matrices. It's a minor point, but it's useful for giving you information about x transpose x without like giving you the entire matrix and telling you to like multiply it. And they have properties like the TSV, the rank being equal to x, and so on. The more important one is the hat matrix, the projection matrix. Okay, sounds good. Okay, a lot of information about linear algebra. Okay, back to the statistics now. I want to calculate the distribution of these estimators. And these distributions are sometimes called sampling distributions. So sampling distribution of beta hat, sampling distribution of sigma hat. These are random variables. They come from the randomness in epsilon. And we would like to calculate these, and these would characterize the uncertainty. So now we're shifting to the abstract view that these are random variables. The first thing that we want to do is to calculate the properties of beta hat. And the first thing is to calculate the expectation of beta. Okay, so let's do this maybe rather quickly here. So beta hat is going to be x transpose x inverse x transpose y. I'm going to call this A. So this is going to be AY. Okay. And let's say I'm going to assume E1. Under E1, expectation of epsilon is 0. Covariance of epsilon is sigma squared. So we saw that the expectation of y, this would imply expectation of y is x beta, because y is x beta plus epsilon. Here, beta is the true beta. If you want, you can put a star on it. And then the covariance of y is sigma squared I, if you remember, because it's a constant shift. So now I want to calculate what the expectation of beta hat is. Can anyone tell me what the expectation of beta hat is? Yes.
There's big beta because the x transpose x is the inverse of x transpose. That's just A. You can just take that
This comes out. Why?
because it's non-random.
Non-random. It's a linear transformation. So linearity or expectation, and the fact that A is non-random. Okay.
And then we know the expectation of y is x beta.
Right.
And then you just plug in this A.
Great. you plug in what A is, which is this part. And then,
And that ends up being code I constant.
yeah, so you can just put parentheses anywhere you want. So you can calculate first this X transpose X, and I also have X transpose X inverse, they cancel out. So this whole thing is going to be identity. So I get beta. So what was your name, by the way? Abel. Okay, good. So as Abel pointed out, the expectation of beta hat is equal to beta. So what can we say? Like statisticians always, this property that expectation of estimator is equal to the quantity that we actually want to estimate. What is it called?
Unbiased.
Unbiasedness. So we would say that beta hat is unbiased. For beta, again, this is an abstract concept. You're not going to see unbiasedness in practice unless you do the experiment many, many times. Then you can look at the values of beta hat that you get on average. So if you average them, let's say, the beta hat, the average would be close to this. And this is going to be equal to beta hat. So the average of those beta hats are going to be hitting beta. Sounds good? So this step is very straightforward once you remember the things that we did about expectations of random vectors, covariance of random vectors under the assumptions and the noise. You can upgrade them to properties of y. And you can see what I'm using here is just expectation of y. I'm not using any distributional assumptions beyond expectation. So E1 is enough to calculate this expectation. And I can also calculate the covariance. So how do we calculate the covariance of beta hat? Let's do that as well. Beta hat is A times Y. Yes.
It's A sigma Y.
A covariance of Y times A transpose. Right? Okay, we plug in, you get sigma squared I. A transpose. How does this simplify? Yeah, so identity is like you can ignore.
Right, but then A.
Yeah, sigma squared also comes out because it's like a scalar.
I think
And then you have to write things down, yes. So you get X transpose, X inverse, X transpose, and then how do I transpose A? I get a little tricky. Reorder, yeah, so you have to like start from the back,
we have
transpose this first, right? So you get X, and then transpose of this. It's the same because it's a symmetric matrix, so I get that. And now what would happen here, some simplification happens, right? I can put parentheses around this. So this is the Gram matrix. Let's say if you want to call it G. This is also G. This is also G. So I basically have sigma squared G inverse G, G inverse. What do I get? G sigma squared G inverse. Or sigma squared like X transpose X inverse. So the covariance matrix of beta hat turns out to be something non-trivial. It's not going to be identity. The covariance matrix of the observation is like that, but the covariance matrix of beta hat is X transpose X unless you have orthogonal design, in which case this Gram matrix is going to be like diagonal. This is going to have non-zero diagonal elements. So the inverse of is proportional to the inverse of the Gram matrix. And also like there is this unknown sigma squared in it. So note that the covariance is sigma squared, the actual sigma squared. Okay, it's not, you can estimate it, but if you want the actual covariance matrix, you don't have it. We have X, but we don't have sigma squared. So the actual covariance matrix, or the actual so the component, the diagonal components of the variances of beta hat, we don't know the variances of beta hat. But we can try to estimate it. Right? How can we get an estimate of this? Yes.
S squared.
Yeah, just we plug in S squared, but this is no longer going to be the actual covariance matrix. It's going to be an estimate of the covariance matrix. Okay, so in practice, what do you do? So Cov beta hat is not observable. Not observable because sigma squared is not observable. But we can estimate it, say by, I'm gonna write it as cov hat beta hat. The covariance itself is an estimate, is gonna be S squared X transpose X inverse. So now this is another random variable. So like a random matrix, because it's random, I get to see a realization of it. In practice, I get a realization of S squared, so I get a realization of this. But this is now also an abstract object. This has properties, so it's still property. But this particular random variable, you can see the realization. That one you can. In some exercises, I ask you for covariance matrix of beta hat. I mean the first one. Even if you don't know sigma squared, just plug in there, just leave sigma squared there. If I ask you for an estimate of the covariance matrix, you can do this. Okay. So there's a distinction between the actual covariance matrix and an estimate of the covariance matrix. Same goes with beta hat. So you can't get the expectation of beta. If you can get the expectation of beta hat, you have beta. You're done. So we don't get to see the expectation of beta hat. But we can actually get an estimate, a reasonable estimate. We also have a reasonable estimate of beta hat. Beta, which is just beta hat. But then that's not the point. But this one we get an interesting like estimate, not trivial estimate of the covariance matrix. And because the covariance, the diagonal elements of the variance of the beta hat, I have the uncertainty or the variability of the individual estimates. Okay, so next time I'm going to come back and hopefully finish. The rest is similar, so you can do the same for fitted values, residuals, and the important thing is actually this, which we hopefully talk about, the joint distribution of beta hat and E, and then talk about inputs. Thank you guys. See you next time.